So thank you very much for the introduction. And it was really nice to be here this week. I learned so many things because I'm not at all a Vertex model style guy. But thanks for the invitation. So what I want to discuss is this system that is called meandric system. I will define immediately what it is. And this is based on a joint work with Ewain, Gwynne, and Minjae Park that are both in Chicago University. OK, let me start by defining the model, motivating why at least I'm interested in the model, and discussing some previous work on the model. So a meandric system is a very simple combinatorial object. It's a collection of disjoint simple loops in the complex plane, which cut the line orthogonally. And if I want a meandric system of size n, the number of cutting points is exactly 2n. And I will look at configuration modulo homeomorphisms of the complex plane, which fixes the line, and are mapping the upper half plane into the upper half plane and the lower half plane in the lower half. OK, if you don't like this definition, in a second I'll give you a second definition. But this is the kind of object that we are looking at.
I didn't hear you said you look at the system modulo something, but
yeah, so in some sense, the configuration do not depend on where you plot the arcs. It's really the arcs that count, what you are connecting, which point. If I deform a bit, this arc is the same.
Oh.
I really look at the combinatorial structure. But let me give you in 1 second a combinatorial definition, and then everything is simple. So this is one special case of a complicated model that is called the crossing fully packed O(n) times m loop model on planar maps. It's not important what is the exact model. The only message that I want to give you is that it's a specific instance of a very general parameter where in this loop model, you plug in 0 in the first parameter and 1 in the second one. This is the only thing that you have to keep in mind and the only important information. And this model has been studied quite a lot in the few past year by Di Francesco and many other co-authors. The first work that I know is by Di Francesco. And I will survey along the walk many of these works. So I won't tell you now what they say, but later on you will see. OK, and what is the most basic question about this object is, how do I sample? There are finitely many configurations. How do I sample one uniformly at random? And this turns out to be exactly the most easy question in the model. Because we have the following bijection. So there is a bijection between meandric system and pair of dig path or walk excursion, if you want. So this is a walk that starts at 0 at time 0, and at 0 at time 0 again, at time n, or 2n. And what you do is the following. Given the walks, I'm going to tell you how you construct the system. So what you do is you take a vertex, you look at the corresponding step, you look at where the walk excursion is ending, you go down and you match. And you do the same operation. Let's do it one more. You go here, you go up, you look where the excursion is ending, you go down and you match. And you do this matching on top using this walk. You do this matching on bottom using this walk. And this is exactly a bijection between pairs of dig path with 2n steps and meandric system of size n. So now the question is simple, because how do you sample one uniformly at random? You sample a uniform dig path at random. If you sample a uniform dig path at random here, you do the matching and you get a uniform meandric system. So, you can always do some Glauber dynamics, or there are infinitely many techniques. You just need to sample a random walk condition to be non-negative and 0 at 0. There are really several different ways of doing it. Exactly. It's the contour function of a boundary. OK, so when you see this kind of thing, you say, oh, the game is nice. Because now, I have a bijection between a system, I have a pair of walks. We know everything about walks. So every question can be rephrased in question about the walks, and so everything should be tractable. It's not true at all. And many questions are completely open, because one of the messages that I want to give you in this talk is that I want to convince you that the loops are an incredibly complicated functional of the two walks. At a certain point, we will see that actually, in the limit, they are not a measurable function of this walk. And I will make it clear. So this is why very basic questions on this system are completely open nowadays. So let me introduce a second infinite volume version of the model. It's very similar. Now what I'm doing is just an infinite meandric system, uniform meandric system. What you do is exactly the same game. But now on top, you have a bi-infinite random walk with step +1 and -1 with probability half. And on bottom, you have an independent b-infinite random walk. And now you do exactly the same game. You take your favorite point, you go up, you see where the excursion is ending, you go down and you match. And you do that for z using the top line, for z again using the bottom line. You match and you get loops. And here it's not even clear if you get only loops or you might get infinite paths, right? It's not automatically true if there are just closed loop or not. And this question is one of the questions that is completely open. So this question was raised by Courrienne, Cosma, Sidora Vishon, and Tournier. And in this paper, what they prove is the following, that either with probability 1, there is exactly one infinite loop, or with probability 1, there are no infinite loops. So they rule out possibility of having multiple loops. They have the 0-1 law, and this is kind of Barton and Keene argument for percolation. It's exactly the Barton and Keene argument adapted to this model. But ruling out the infinite cluster is completely open. Okay, why I care about this model? So my motivation are coming from a very old question in mathematics that is a question of Henri Poincaré in 1912. He asked, in how many ways a simple loop in the plane can cross a line at a specified number of points? So in modern language, after Vladimir Arnold, these are called meanders. So a meander is the following combinatorial structure. I give you a line. I give you 2 endpoints. Here are 12 points. And I ask you in how many ways a simple loop can cross this line exactly at these 2 endpoints. So in our language, how many meandric systems of size 2n have exactly one loop? OK, so for people that like topology, this is exactly the same question of saying I take 2 journal loops on the sphere, and I condition them to cut orthogonally at 2 endpoints. I root them and orient them, and I want to count how many topologically inequivalent configurations are there. OK, good question. So the question is, what are the numbers here? So the first number are just numbering the points following the line. Okay, and the second one is renumbering the black one following the loop. So it's 1, 2, 3, 4, 5, 6, and so on. But I won't need it in this talk, so you can completely forget. It's just because this structure can be encoded by certain permutations that are called meandric permutation, and these are exactly the permutation, but I don't use it in this talk. So why I'm interested in meandric system? Because, again, this is a particular case. This is the real question where I started to get used to this model. And again, this is another form of the same crossing fully packed loop model on planar maps, but now the 2 parameters are 0, 0. And we have a second paper that I won't discuss here where we have work related to this meander setting. But today I will just discuss meandric system. But this was our motivation to study. The hope is that understanding meandric system will help us to understand what's going on also in this model. And a priori, they should be a bit easier. Okay, so here are some natural questions on meandric system that you might want to answer. But keep in mind that the loops are complicated functionals of the books. So the first question is, if I sample uniformly at random one meandric system of size 2n, how many loops are there? Then, if you can access this question, maybe you want to know what is the size of the largest loop. You see a very big loop, you see very tiny loop, you see loops that are of macroscopic size, and I will clarify what I mean. And if you know what is the loop of the size of the largest one, do you expect that there is one that is very big and all the other ones are small, or more or less the first one and the second one are kind of comparable? And obviously, the question that I really like is, can we describe the scaling limit of this? Can we describe the full geometry of the system?
So this is assuming uniform measure on the dict path.
Exactly. Random dict path, independent random dict path at the bottom. You match, and you want to answer one of these questions. So it's fair to say that the first question is completely solved, more or less, up to something, by Ferré et Ewain, where they show that if you take the number of loops in a meandric system of size n, you divide by n, you converge in probability to a deterministic constant t. And what is already interesting is that c is a constant that can be expressed as a sum of weights, and the sum is over meanders, not meandric systems. So there is already a connection between meandric systems and meanders in this work. And determining the exact value of C is an open question. They have very, very good upper and lower bounds. But the exact value of C is open. There are very good numerical simulations. There are rather complicated expression as sum of certain weights. And there is a very recent result where they showed that the weights are always rational polynomial in 1 over pi. It has been proved, but computing the total sum is open. There is a numerical value, 0.5 something. I don't remember. I can look into that, but I don't remember. It's a number that doesn't look nice, at least. But you never know. So the second question was addressed by Karjin, at least the most recent result that I know is by Karjin, where he proved that the largest loop contains at least log n points. So he showed that at least the largest loop is growing with n. And then he did a numerical simulation and he said, OK, my result is not very good because I see that the largest loop is like n to the alpha, and alpha is very, very close to 4 over 5. And so he conjectured that the size of the largest loop is n to the alpha with alpha 4 over 5, but based completely on numerical simulations. So this third question is very, very related to, at least the first step to address this question would be to rule out that there is no infinite loop in this infinite volume version. And actually, this is what is conjectured in the paper of Kurian and co-authors. They conjecture that there should not be the infinite loop. But there are no explanation, and actually we emailed them, and they said that they don't have a very clear motivation why they don't believe that it shouldn't there. They said, OK, if we have to guess, it's not there, but we don't have any heuristic argument to justify why it shouldn't there. And actually, in their paper, the conjecture is stated in a more general setting when you have just ergoding and translation invariant arc system on top and bottom. And for the last question, as far as I know, there was no conjecture available. OK, so the goal of the rest of the...
Why don't you want to know how many meanders there are? I mean, with one loop.
How many what?
Meanders?
The number.
A meander is a loop.
Why don't you?
How many meanders?
Why don't you ask how many there are?
I mean, it's Catalan number
No.
squared, the number of meandric systems, the number of meander with one loop. Yeah, this is another talk. I really care about this question. The motivation why I'm working on this model is to answer that question in the very long term. But this is an incredibly open question, and I don't think understanding meandric system would be enough. I think it's really like in the level of difficulty, this is the toy example that you do to understand the theory, in my opinion. Meandric systems should be much easier than meanders. But yeah, the number of meanders is the very old question of Henri Poincaré, and there is a remarkable conjecture of Philippe Di Francesco, Golinelli, and Goutier about what should be the growth, Guiter, sorry, about what should be the asymptotic behavior of this. They predicted what should be the critical exponent for the asymptotic growth. But yeah, another talk, I'm not discussing this here. So what I want to discuss here is some conjectures about this model, some new conjecture, some rigorous results that are going in the direction of this conjecture. And finally, I'll ask you some questions. OK, so we take this new point of view on a meandric system. So you take a meandric system, and you look at this as a planar map. So as a graph embedded in the plane in such a way that no edges are crossing. So the vertices of the graph are the 2n integer points. And the edges of the graphs are either the arcs or the pieces of the line connecting points. And then you identify this final piece with the final piece there. So you have the topology of the sphere. OK, so this is the planar map, and I will denote the planar map by Mn. Then on top of this planar map, you have an Hamiltonian path, which is given by the line. And this is really just a path that is visiting all the vertices of the graph exactly once. And finally, you have the collection of loops. OK, so I will re-look at this combinatorial structure now as a triplet, a planar map, an Hamiltonian path, and a collection of loops. Obviously, if I give you, for example, the planar map and the Hamiltonian path, you immediately determine what is the loops, and vice versa. If I give you the planar map and the loops, you immediately determine what is the Hamiltonian path. So they're not independent. OK, here is the conjecture. So in the conjecture, I need 3 types of object. The first object is a gamma Liouville quantum gravity measure and metric. The second object is an SLE, and the third object is a CLE, a Schramm-Loevner evolution and a conformal loop ensemble. So I'm not assuming that you know any of them. And I will define them as scaling limit of certain natural discrete models, because I think it's the best way to get an intuition on what are these objects. But I want to stress out that they have their own definition directly in the continuum. But I won't define them like that. And the classical example is, if I want to define Brownian motion, I can define Brownian motion, say it's the only stochastic process, blah, 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 blah. Or I can just say it's the scaling limit of simple random walks. And I will take this point of view. OK, what is gamma LQG measure, and what is gamma LQG metric? OK, let's start with a random uniform triangulation over n vertices. So you have n vertices, and you take uniformly at random a triangulation. So a planar map with n vertices where each face is a triangle, including the external face that is a face, because we are always in this talk on the topology of the sphere. And now you embedded on the sphere in a certain canonical way. I don't want to enter in the details. There are many ways of doing that. Using circle packing, using Tat embedding, using the Smith embedding or the card embedding. I think in the sphere, the best one is this Smith embedding. Tat embedding works well in the disk. But without think that the planar map is embedded on the plane in a very canonical way. And obviously now you have a new notion of distance on the plane. You fix two vertices, and you're saying that the distance between the two vertices is the shortest path in the graph that you can take to go from U to V. So in this specific example, the distance is 3, 1, 2, and 3. And there are no shorter paths to go from U to V. This is the metric at the discrete level. What is the measure? You fix a set in the complex plane or in the sphere, and you say that the measure of this set is exactly how many points of the planar map are falling inside this set. So in particular, in this set, you have 4 points, so the measure of A is 4. And then one can prove that rescaling the measure by a factor 1 over n, and rescaling the distance by a factor 1 over n to the 1/4, you converge in distribution when n tends to infinity to a random measure and a random metric on the sphere. And the random measure is called the square root of 8/3 Liouville quantum gravity measure. And the limiting metric is called this LQG metric. OK, the specific parameter is not really important for the talk. You just think that there is a one parameter family, and the intuition that you have is if I change a bit the law of the triangulation, like I reweight by Boltzmann weight or something like that. Maybe Boltzmann weight is not enough, but I reweight by some statistical mechanics model on the planar map, I can change a bit this parameter, but it's the same universality class. For people that love more central charges, this is central charge 0. And this has been proved, at least for this specific embedding and for the topology of the triangle, by Nina Holden and Shin Soon in an astonishing recent paper.
And using different embedding, you get different results?
No, at least. The conjecture is that these results should be very, very universal. In the sense, OK, you need some regularity, obviously, on the embedding. But if the embedding is natural, the thing that you really need is that you want that each phase become microscopic. This is more or less what you need. It's believed that the limit is always the same. It's really a universal family of. But
you need some kind of conformality.
Exactly. You need that. These objects are all conformal invariant or covariant. And so you need to preserve this property. Thanks, Rick. I want to make a side note because it will be useful later. So one can easily show that the diameter of a triangulation, one can show that the diameter of a random triangulation on n vertices is roughly n to the 1/4. That is why I'm rescaling like that. And I want to stress that this is related to the fact that we know that the Hausdorff dimension of this limiting metric space is exactly 4. So if you take a ball of radius r, you expect r to the 4th point, or a volume of r to the 4th. It's like a 4-dimensional space, but has the topology of the sphere. It's a very fractal space. OK, this is LQG. What is SLE? You take the square lattice, you take a uniform spanning tree, and you turn around this spanning tree. So what I'm doing is just traveling around the spanning tree. And you get a space filling curve on the lattice. You send the mesh of the lattice to infinity, and you converge to a limiting space filling curve that is the limit of this blue curve that is called SLE8. So it's a random space filling curve. That's very nice property, and this has been proved by Lawler, Schramm, and Werner. And this is the second player in the game, is this space filling curve that you see here. And the central charge, if you want, is -2. Third object, take the hexagonal lattice, do critical Bernoulli percolation. We're all experts now. And you take the contour of the clusters. So in red, I'm just taking the contours of clusters. So this is going to give you, in the complex plane, a series of loops. And loops can contain other loops because cluster can be one inside the other. You take the scaling limit when the mesh of the lattice goes to 0. And Smirnov proved that in the limit, you see that these loops converge to some random loop. And the collection of this random loop is called conformal loop ensemble of parameter 6. And the central charge here is 0. OK, so our conjecture is the following. Remember, we are looking at a meandric system as a planar map plus Hamiltonian path plus collection of loops. The conjecture that we have with Ewain and Minjae is that this triplet, after an appropriate rescaling, converges in the limit to the following triplet. In the first, you have this LQG measure and metric coming from the planar map. And the value is conjectured to be square root of 2. The path converges to this SLE8, same as contour of spanning tree. And the collection of loops is exactly as percolation, conformal loop ensemble 6. And I want to stress that the conjecture is saying that these three objects are independent in the limit, which is not at all obvious because, as I said, if I take two elements here, they exactly determine the third one. I will comment on that later. But the conjecture is saying that they are independent. So I don't want to, it's a conjecture, so who cares about what type of convergence? I think it's very, very general, but I would be very happy if you take the weakest convergence that you like and you prove this. I don't care really about what type of convergence. So for expert, this is the same pair that you get if you take a uniform planar map reweighted by a spanning tree. And OK, the second one is exactly critical percolation. And here are the central charges. Just one remark, note that the sum of these is exactly this one, which is not a coincidence. OK, to be fair, this is just a sort of rephrasing of work of DiFrancesco and co-authors about this crossing fully packed O(n) times m loop model on planar maps. So there is this paper around 2000 where they were motivated about giving a conjecture for the growth of the enumeration of meanders, but looking at their reasoning and rephrasing their reasoning in terms of LQG, SLE, and CLE, most of these objects, they were not even there in 2000. So that's why it's not even phrased in that language, but we rephrase their conjecture, and we get our conjecture. But I will give you at least two more heuristics why we believe in this conjecture. One will be included at the end of my talk, and I will tell you. And the second one is based on several numerical simulations that you can find in our paper. Why? Given this conjecture, you can predict a lot of exponents about this meandric system. And we computed them using this KPZ relation. And we tested them. And all of them are matching exactly our predictions. OK, what you see here is just to give you an idea of how you can get something like that. So here, there is a meandric system of very large size, like, I don't remember, but something like 10,000 points. And the colors, in red, you see the largest loop. In orange, the second largest loop, and so on. And we color just the first 300, because then it was getting crazy, the computer. And what we did is to embed, now you have a planar map. We embedded the planar map in the sphere. OK, looks like a disk, in such a way that each point is exactly the body center of the neighbors. This is what is called the TAT embedding. So it's one canonical way. And as you can see, you start to see that these loops, first of all, they look very macroscopic. And secondly, they look very fractal. So what you see here is in gray, you see the planar map, and on top, you see the loops. So what about the SLE? So in this second simulation, what we did is we color the points here from blue to gray to green, and then yellow, orange, and so on. And we recolor the faces, the corresponding faces, using this coloring. And as you can see, you should expect that you get a certain space filling curve that is moving around the space in time, going through this color. And this is what we expect to be the limiting SLE8. It's a space filling curve, so it's coloring everything. OK, so one remark. The fact that the first pair, planar map and Hamiltonian path, converges to square root of 2 LQG and SLE8 is known at least in a weak sense, in the pianosphere sense. It's a very weak, it's not a topology, but it's one way that we have now in order to at least prove in some sense that a planar map with some model is converging to LQG and SLE. It's too complicated to tell you how it's defined, but it has an important consequence that this fact, the fact that we can prove this, plus some work of Ewain, Nina, Holden, and Shin, gives us immediately the following result. This is a rigorous result. That the planar map Mn has a diameter that is n to the 1 over d modulo log correction. And this 1 over d is, we know what is this value. D is exactly the Hausdorff dimension of the square root of 2 Liouville quantum gravity. So this is an analog. Before, the Hausdorff dimension was 4, and that the diameter was 1 over 4. Now the dimension is d, and the diameter is 1 over d. So what do we know about d? First of all, we know that it's almost surely deterministic. So it's always the same. It's not a random parameter. And these are the best rigorous lower and upper bound on this value. So we don't know the exact value of d, but we have fairly good upper and lower bounds. So from now on, you should imagine that, yeah?
Sorry, I just want to get the notation. Mn is the square root of 2 LQG with the SLE8 on it?
No, Mn is the planar map given by a meandric system of size 2n. Yeah. But whatever system of planar map plus path that you know it's converging there in this sense, okay, in the pianosphere sense, you are proving that the pair of random walks that encode this planar map is converging to the limiting. And then you use this KMT coupling to get this result. So what I was saying is that now we know that we live in a space where the diameter is typically n to the 1 over d. So if we want to prove that the loops are big, we should prove that at least they are proportional to this diameter, at least. They might be much longer, but otherwise, when we take a scaling limit, we kill them, because this is roughly the right rescaling. OK, so what are the consequences, first of all, of what I said? OK, obviously, now we have a conjectural scaling limit. But not only that, so for example, remember this n to the 4 over 5 of Karjin? Using KPZ, we can replace this conjecture by saying that the exact value should be n to the alpha, and alpha is not 4 over 5, is 3 minus square root of 2 divided by 2, which is very close to 4 over 5, is 0.792, but we believe that this is the right exponent. And this is coming from measuring what is the Hausdorff dimension of a CLE loop using the square root of 2 LQG metric. And finally, Yeah. I mean, it's a corollary of a conjecture. It's a conjollary, if you want. Yeah.
So there's no k on the right-hand side. Right? This is the vertices of the kth Largest loop, but then it's approximately something that is.
No, OK, I didn't underline that. We believe that if you fix k and you look at the size of like 10. If you look at how many points are in the 10th largest loop, you're still of this order.
Okay, so like all the large,
all the
finitely many largest loops are of the same order as
exactly.
the one term.
So this is not saying only that the biggest loop is like that, but we believe that there are many of them of this order. And this is what you also was noticing from the simulations. And obviously, since we know that in the conformal loop ensemble 6 there are no infinite loops, this is a heuristic explanation on why we do expect that there are no infinite loops in this model. So this is giving a justification. And finally, I want to stress that we have numerical simulations supporting these heuristics. Okay, what are the theorems that we can prove? Okay, the first theorem that we can prove is the following. Let again, this Hausdorff dimension, this number that I introduced before, we can prove that the number of vertices in the largest loop in the collection of loop is at least n to the 1 over d plus log correction. So there are loops that are as long as the diameter of the map. So this is kind of saying that there should be big loop. And if you want the number, it's here. So I decided not to give you the proof because it's 5:30 at the 4th day of a conference, and I think no one wants to see a full proof now. But let me give you two words on that. The proof is divided in 2 big steps. The first step is completely discrete probability. What you do is you prove that there are loops that are big compared to the size of the planar map. And then the second step is using SLE and LQG techniques, we can say, okay, since the loop are very close to the diameter of the map and we can control very good the diameter of the map, we can conclude that this is true. But here, in the second step, we use 2 big tools. One is the mating of trees of Scott and Jason, and the second one is the recent construction of the LQG metric. So I would say this is elementary but tricky, and this is using very big tools. But if you know the tools, it's quite automatic once you have this first step.
Excuse me? So what you are saying is that the Peano topology is enough here to convert.
Say it again, sorry.
I mean, so you need some conversion statement of discrete to continuum, and the Peano sense is enough.
Exactly. The Peano sphere, despite being very weak, it's enough to prove rigorously, to get back rigorous result like that. The O1 here, it's exactly one consequence of this. We use KMT coupling, and this KMT coupling does not rule out this O of 1 possible correction. So I want to stress 2 things. So this theorem is telling that there are almost macroscopic loops. This almost is related to we don't know if there are log correction. But on the other hand, it's very far from the conjecture. Remember that the conjecture is with this very strange alpha, which is like 0.79, and we are able to go just here. Okay, even if we improve the bounds, we will never get there. But it's much better than the previous log n. So now we have polynomial bounds. And I want to stress that it's not because we didn't do careful estimate with the exponent that we didn't go here. It's really a completely different problem to go here. Because in some sense, we proved that a loop is at least as long as a geodesic. And now to go here, you need to prove that a loop is much longer than a geodesic. So you really need to access to the geometry of this loop, which at the moment is completely out of reach. Okay, the second result.
So this loop is related to SCI sense?
Yeah, conjecturally.
Yeah, so I mean, consuming your conjecture, can you improve this one?
Assuming the conjecture, we can prove that it's exactly n to the alpha. Maybe we have still this little o of 1, but yeah, we can get very close. The second result is in the other direction. Now, the previous result was saying there are big loops. The second result is telling you at least under some operation, there should be no infinite loops. So what we prove is the following, that if you take the infinite meandric system, you take your pair of scissors, and you cut all the loops along this ray. So you cut here, and whenever you cut all these arcs, and I want to stress that there are infinitely many ones, what you do this rewiring operation. So the first one that has been cut, you reglue on the left with the second one, the third one with the fourth one, and you redo the same with the other one. What we prove is that after this operation, almost surely there are no infinite loops. So if you want to have an intuition on what it's saying exactly that if you take Bernoulli percolation on the plane, and you remove a ray from the origin, there is no infinite cluster. Or in 3 dimensions, I think it's known that in the first octant there is no infinite cluster, but it's still open that in 3 dimensions there is no infinite cluster in the world space. This is kind of the analog. We know that in an octant there is no infinite cluster, but we cannot rewire things and rule out. So the very general question is still open. OK. From now on, nothing is rigorous. So I will try to tell you what I think are the interesting questions of the model, what I think are the difficulties, what I think are the direction on how we might overcome these difficulties. I'm really speculating on that. But maybe some of you come back with some idea that is better than mine, and I would be happy to discuss. So remember that a meandric system can be encoded by this pair of walk. Let's call the top walk xn and the top bottom walk yn. So the fact that xn, yn converge, obviously, to a 2-dimensional Brownian motion in the infinite volume version, or to a 2-dimensional Brownian excursion in the finite volume version, gives immediately, using this mating of trees, this convergence of the first triplet, of the first pair, to the first pair in this Peano sense. And this is rigorous. So the key point of this step is to prove, and this was done by Duplantier, Miller, and Sheffield, to prove that this pair x and y actually determines the pair SLE LQG, and the pair SLE LQG determines x and y. So these two things are in bijection in the limit. Now, our conjecture is saying that the triplet converges to the triplet. OK, but this first part is kind of rigorous, at least in the Peano sense. And now, believe for a moment that in the limit you get a CLE, which is independent. Then we discuss on that. And you ask, what is the only possible value of kappa? So you immediately see that the planar map has a central charge that is -2. And there is a general belief that is saying that the general map, the central charge of the map that you see in the limit, should be exactly the sum of the statistical mechanics model that you put on that to reweight the law of the map. And this is known, for example, in the first pair, you reweight, you don't get a uniform map, but you get this uniform map because you're reweighting by this. So if you don't want to reweight more, the only thing that you can put here is central charge 0. And so this fixes the value of kappa to 6. This is one possible way of arguing why at least we believe that kappa should be exactly 6. Because you don't see any further reweighting here. If you have a different kappa, central charge should be not 0, and you should see here the sum of the two central charges. OK. The question is why the CLE 6 should be independent. This is less obvious. So remember,
Correct to say, sorry for interrupting, that you already used this assumption, right? Because of computation.
I mean, I use this one,
Oh,
but I never use the fact that here we have a CLE 6.
Why then should we add central charges if they're not independent?
Say it again, sorry.
Imagine that they're not independent. Why do we?
Exactly. If they are not independent, I said, let's argue assuming that they are independent. And then we get, and now I'm going to tell you why I believe they are independent. No. Questions are very welcome. Okay, so the pair XY determines the pair LQG SLE. So obviously, we use all the randomness. It's over. We have no more randomness. Where is the CLE6? It's telling you that the CLE6 is not at all a measurable function of x and y. So here, again, the loops are a terrible functional of the walks. So we need, what we believe is that we need to keep track of more information. And we really believe that this additional information is completely independent. Because you don't have any information here for the CLE6. But at the discrete level, everything is so strongly coupled that you say, OK, this looks like a contradiction. But let me convince, there is hope. There is hope. The hope is the following. Look at these two meandric systems. They look pretty different, right? One has very few loops. The other one has a very big loop here. Look at these. The only thing that I did was to translate by one the bottom walk. So at least this, to me, intuitively is saying that if you perturb a tiny, tiny bit the walk, you should not change at all the scaling limit of the Brownian motion. But you should almost completely resample the CLE6. So to me, at least this is a very good motivation to behave that everything is independent in the limit. In the sense that what I would like really to prove, and we are working on that, but seems to be a very tiny problem, is that remixing a little bit the walk will completely remix the loops, but will not change the limiting Brownian motion. I strongly believe that it might be really possible just shifting a bit. And this is not even mixing the walk, it's just translating. But OK, it's completely open, this. But this is the thing that I really would like to do. I think one very useful step is to prove this fact, that it's enough to mix the walk a little bit in order to completely mix the loops, but not changing the LQG and SLE. Yeah.
Really consider this as a small perturbation because you are actually doing some global shift here.
Yeah, but if I have a random walk, okay, between 0 and 2n, and I shift by 1, the scaling limit between 0 and 2n is more or less identical, right? So it's very big in terms of loop, but I think it's very small in terms of random walk.
So I was thinking with a very small other type of perturbation, which is really local here.
I think this operation is not the right one, at least if we want to prove. What I would like to do is doing this local minima or local maxima flipping. This is what we are trying to do. But it looks hard. In some sense, you have to access to the pivotal point of the CLE6, but we don't know that is a CLE6, so we don't know where are these pivotal points, and everything is a mess. OK, CLE6 percolation, where are you? We didn't see any percolation so far in this model. So here it's a proposal, or at least where I believe it's the percolation. So take a meandric system, and at this point, you add a middle integer point, and you color green, orange, green, orange, green, orange, or yellow, whatever it is. And now you do the following. You look at the orange, and every orange is matched with the next orange that you can match without crossing red edges. Okay, and here we cannot match anything because we are blocked by red. And then you do exactly the same with green. So green is matched with this green, with this green, with this green, and in the other case with this one. But this one is matched with nothing because it's blocked by red. And now you start to see percolation. You think about green to be open, orange to be closed, and These are just the boundaries of the clusters. OK, this is not very satisfactory. Let me give you 2 more bits that maybe are starting to convince you that something like that might go on. So every orange edge has 4 potential edges, right? Left, right. These 4 potential edges. Now, what you do is the following. Take a vertex and sample uniformly at random each edge with probability 1/2. And you get such a configuration. And you interpret that this means that it's open the edge, and if it's not there, it's closed. And now what you do is you match these alpha edges in the only way that the configuration remains planar. This, I claim, that determines everything, in the sense that now you match green in the only possible way you can match green without crossing orange. And then you do the boundary of the clusters. And what you can prove is that if you start with this law, the law of the red loops are exactly a uniform meandric system. So here I think this is the good interpretation, in my opinion, as percolation. The percolation is really on these alpha edges. That's how you sample it. OK, we have percolation. What is the first question that you ask? What is a crossing probability? So what we proved, and it's very easy to prove, is that if you fix a box of size n, starting at red and ending at green, and n is the number of white vertices that you have inside, the probability of having a red path that is going from here to there, so top left to bottom right, is exactly 1/2. So, and the argument is exactly percolation. If there is not this one, there is a green one that is going in the other direction. And so by symmetry is 1/2. OK, so far it looks very promising. And then you cry. Because you can prove that this crossing event, they do not have FKG. And actually, I conjecture that they are anti-correlated. And I don't want to discuss on why. If you want to know why, I can discuss later. It's a bit a fact. It's related to the fact that this box is random, actually.
So this red should be yellow, right? From the previous picture.
Yeah, you're completely right. Sorry, this should be yellow. Sorry. Final slide. I would really love to have integrability. I don't know why people say, I don't like that the model is integrable. I would love if the model is integrable, because it would really help us. And here it's the only very integrable result that I know about this model. So Di Francesco in '98 proved the following. If you take the following matrix, Mn, it's defined like that. Columns and rows are indexed by dict path. So D1, Dcn is an enumeration of the dict path of size n. And in each coordinate, you have the following quantity. You look at the entrance ij. You take the dict path I, you take the dict path j, you do the operation, you count how many loops are there, and then you put as an entrance q to the number of loops. So if di and dj are these two things, you put q to the 2, so typo. And what it shows is that the determinant of this matrix is very nice. In the sense it's just the product of certain Chebyshev polynomial raised to a linear combination of certain binomial coefficient. So this is so beautiful that I was frustrated not to be able to use it. So I tried, and so far I always fail, but I would really try to use this result to prove something. I can't believe that it's so beautiful and you are not able to say some geometric consequence on the model. But first of all, I'm not very expert on these determinantal structures. But I think this is the right community. If any of you have any idea on how to apply these to any of the questions that I raised, I would be very, very happy to listen. Q is a parameter. No. Here there is no Q. Here is how they are defined. Here it's just how they are defined. Yeah. It's just the definition of this polynomial. Okay, thank you very much.